Hi, this is the team breakdown of Group H. We have three computer engineers. The first is Yusuf, then we have Dominic, we have Brendan, and then our fourth member, Christopher, is our EE.
Hi, my name is Chris Clifford. I'm the project lead for Group H. We're designing the pin transfer chemical screening robot. So, I'm going to talk a bit about what inspired this project, how we went about doing this project, and the results of our project, how we met our technical specifications that we sought out to meet. So, for a bit of a background, I'm interested in type 1 diabetes research, and I've done a couple internships up in Minnesota at the Mayo Clinic, where I have conducted manual chemical screens on differentiating beta cells, which are relevant in type 1 diabetes. So, the reason I do these chemical screens is to see if we just throw a bunch of different chemicals that we have no idea how they affect these cells, what do they do to these cells as they grow? So this is really scalable, and there's some labs that will use robots to do this because it's so scalable and it's such a repetitive process. Most of the labs that don't use robots for this process is because it's just monetarily kind of exclusive. So my goal with this project was to make a robot that does what I do, but make it affordable enough so that labs that are like mine that are dealing with novel diseases or diseases that affect a small subset of the population and therefore have limited funding have a way to conduct these kinds of chemical screens that don't require access to some of the larger labs like at the NIH that are extremely expensive with huge robotics that just aren't accessible to these kinds of biology labs. So now that I've talked about the motivation, I'm going to talk a bit about pin transfer tools. These are the tools that we use to do these chemical screens. Basically, they're replicators. So if you have a standard format microplate, which can have 96 wells or 384 wells in them, all of these wells are separate from each other. So you can have cells in these wells and they're all separate from each other. Well, a pin tool goes in, one pin goes into each of those wells, and when you dip the pin tool in, it takes whatever liquid was in that well, it takes a very small amount of it and moves it out, and then you can dip it into another microplate and transfer that. So it puts a very diluted amount of that chemical or solution into a different microplate. So there's a manual version of the pin tool, which is what I use, and it has its obvious limitations. Like repeating results and experiments is very hard because every single time you use it, it's a bit different. Also, it's very time and labor intensive. So the next thing you could do is you could get a liquid handling conversion kit. So a liquid handling conversion kit goes on a liquid handling robot. These are robots that have pipetters attached to them, and they're generally used just for moving liquid from one reservoir to the other, but larger amounts of liquid. So you can take the pipette head off and put a robotic pin tool on it, and there's companies that sell this adaptation, and they can cost at a minimum around $10,000. So they're still pretty expensive, and they have their own limitations. Some of the limitations are that liquid handling robots generally don't have any kind of way to move plates. So if you want to do more than one pin transfer, if you want to load in multiple microplates at the same time, it can't handle that because it doesn't have any kind of robotic gripper or robotic arm. So you can only do one at a time, which kind of defeats the purpose in my perspective. Um, then you can go up beyond a liquid handling conversion kit, and that's like industrial robots I was talking about, like at the National Institutes of Health or Harvard or other huge biomedical laboratories. It can cost millions of dollars, and they're really not accessible to certain labs that don't have the funding. And not only that, it's overkill for some of the experiments that need to be done. So if we could have a robot that's similar to liquid handling conversion kits that is cheaper and they can also deal with multiple plates at the same time, that would be amazing for these laboratories, and that's what we sought out to do. So the standard format microplates can hold up to 96 different chemicals, which is what we were using in our experiment. And after these chemicals are moved from the source plate to the recipient plate, the pin tool needs to be washed and dried between each of these cycles. So to wash it, generally the procedure is to dip into about 3 different solvents, which can be DI water, DMSO, and 70% ethanol. It's pretty common. So that's kind of what we one of the requirements that we set for our robot was that it could do 3 different wash steps with 3 different solvents, and then after that move over a drying fan and to dry the pin tool. And I'm happy to say that we accomplished that. We have 3 different wash reservoirs on our robot, and we have a drying fan that is mounted to a milled aluminum plate which is raised above the base of the robot so that it allows for airflow into the drying fan, and that works great. Additionally, we use a robotic pin tool, which is slightly different than a manual pin tool. The difference is that the pins are free to slide in a fixture, so if the robot does happen to go past its Z limits, the pins won't get damaged. They'll slide up into their fixtures, so that's a safety precaution to not damage the equipment. And another technical requirement that we have on our robot is that it needs to be able to fit in a biosafety cabinet. Biosafety cabinets are used in research laboratories to protect the operator and the biologics from being contaminated. So it produces a laminar flow of air in between the operator and the workspace, which prevents any airborne particles from entering through the barrier. So this had a certain dimension to it, and we had to meet that. So we managed to closely meet that. 2 of our axes are a couple inches over the dimension, but we can easily make our robot fit the dimensions by cutting our linear actuators. We gave ourselves extra room while we were prototyping, and we can shorten the robot in these dimensions by just cutting down on the linear actuators, because we don't use the full range of motion on them currently. So I would say that we met those technical specifications. Then just in general, our robotic design is like a 3-axis CNC robot at its core with 2 Z-axis heads that slide on 1 Y-axis. The benefit of having 2 Z-axis heads is that we can use up more of our workspace. If you have 2 different heads, meaning our parallel gripper and our pin tool on the same Z-axis, then you can't raise them independently, which means that you always have to think about where those are going to be while you're using the other end effector, which makes you take up more room on the robotic workspace so that you don't bump things as you move around. So to solve this, we use 2 independent Z-axes so we can pull up the one we're not using while we're using the other and be more efficient with our space so that we can make a smaller dimension robot. So that works great. The mounts that were designed for the pin tool and the gripper, I had to design myself so that they could be screwed into our C-beam rails. I had to mill clearance holes and thread T-nuts so that we could make sure that they're always held at a flat plane compared to the base, so all the pins go in at the same depth and that the gripper can grip the plates appropriately. Our stacking design, so we went through many iterations for this to figure out the best way to do it, and what we arrived on was milling out acrylic at about 4/100ths of an inch. And what this allows is the microplates have a small lip at the bottom, at the base of them, so the outline, the perimeter of the microplate can sit in a little milled seat so that it can't slide in the X and Y plane. So this works really well. It allows the gripper to always go to the same coordinate and pick up the plates, same with the pin tool. Eventually, right now it is a 3mm sheet of acrylic screwed into MDF. It's going to be just 1 sheet of aluminum that I'm going to mill, but because of the manufacturing, how hard it is to manufacture and how long it would take to manufacture, right now we're currently just using acrylic in MDF, and that works great, but it isn't as easy to keep sanitized with MDF, so that obviously will have to change and be aluminum eventually. And we said that we would have a failure rate of less than 1%, and we definitely have achieved that. The robot's extremely reliable, and it doesn't drop plates, which is great. Otherwise that would defeat the purpose of the robot. We have an emergency shut-off button for safety, which works properly and cuts power to the microprocessor. It stops all of the motors, and we can handle up to 8 microplates at a time. So that's 8 microplates in the chemical input stack and 8 microplates in the recipient input stack, which is great. That means that it can do up to 8 pin transfers, and the scientists can leave, check their phone, and they'll get a push notification whenever all 8 plates have been processed, and they can come back, unload them, and they could do another run if they wanted to, or they can put the robot away. So that's great, and Mayo Clinic loves that.
You can see in this hardware block diagram, power runs from the 120 volt wall outlet to the 24 volt power supply. The power supply is then connected to an e-stop button. This gets the researcher a way to safely disconnect the pin transfer robot at any point during its operation. The emergency stop button connects it to DC to DC converters, as well as all 5 motor drivers used to operate the motors. The 24 to 7 volt buck converter sends power to the parallel gripper's servo motor, while the 24 to 5 volt converter is used to operate the Atmega 2560 chip. From there, 2 motor drivers are used to power the 2 X-axis motors used to move the gantry. A 3rd motor driver is used to operate the screw-driven Y-axis linear actuator, while the 4th and 5th are used to operate the screw-driven Z-axis linear actuators used to move the pin tool and parallel gripper, respectively. This leaves the Atmega 2560 responsible for communicating with the LCD and Bluetooth modules, as well as with the 2 MOSFETs used to power the drying fan. This software block diagram provides an outline for the flow of the program. The program starts with the LCD asking the user for the number of weld plates, the depth at which the pin tool will be inserted, as well as the number of wash steps that will be used to operate the robot for the entire pin transfer process. The user is then asked to confirm the parameters provided before proceeding. Upon confirmation, the HM10 BLE module will connect to the Progress Monitor app and begin sending updates to the researcher on the progress of the pin transfer robot. This also marks the beginning of the motor calibration process. From there, the source and recipient microplates will be unloaded from their respective stacks to the staging area, where a pin transfer operation will take place. After the pin transfer operation has completed, the microplates will be loaded into their respective output stacks. Lastly, the pin tool is dipped into the wash reservoirs and dried. This process repeats itself until there are no more plates left to process from the input stack. Once all the pin transfer cycles are complete, the BLE module notifies the researcher that the pin transfer process has concluded. From there, the LCD will prompt the researcher on whether or not they would like to perform another pin transfer cycle or set of pin transfer cycles, or simply terminate the program. For budgeting, the majority of our expenditures went to assembly parts for a pin transfer robot, as well as electronics that were used in the PCB, making a total of $1980. The pin tool also cost about $37.70.
NEMA stepper motors are motors that can accurately step to a given position. There are different types of NEMA motors depending on the amount of torque and force needed to operate the given application. For our robot, we went with the NEMA 17 and NEMA 23 motors. In brief, 2 NEMA 17 motors are used to move the entire gantry across the x-axis. This can be seen in the picture below. NEMA 23 motors are used for both the y-axis linear actuators and the 2 z-axis linear actuators, also seen in the image below.
Motor drivers are needed to control the stepper motors in an easier manner. For this robot, we chose to use the DM542T motor drivers for their high resolution of control from between 400 to 25,600 steps per revolution. Interfacing with the motor drivers is simple by only using 2 pins on a microcontroller. A linear actuator is a device that consists of a linear rail body, such as a V-slot linear rail or a C-beam linear rail, and a motor that drives either a belt or a lead screw. This is used to move a gantry cart across the rail. For our robot, we have 2 linear actuators for the x-axis, 1 linear actuator for the y-axis, and 2 linear actuators for the z-axis. With all of this, we can move the pin tool and gripper in all 3 axes of motion to position them anywhere in the workspace of the robot. Although stepper motors are highly accurate, it is necessary to calibrate the motors somehow in order to determine some home position such that the motors know where they are. To do this, we are using mechanical limit switches, which are activated when the gantry cart comes into contact with the lever arm of the limit switch. After the robot turns on and the user inputs cycle data into the user interface, the robot will commence its calibration stage, where each linear actuator will move towards its limit switch. This will allow us to have some reference position in our code to accurately move to predetermined destinations for operation. To power all the components of the project, we need a suitable power supply. According to the power delivery needed for the circuit, as referenced in the table below, we need at least 350 watts of power when the robot is drawing the most power. To deliver this, we are using a Meanwell 24-volt power supply unit. This is a suitable unit for delivering all power to each of the motors, parallel gripper, and the fan heater, all at the same time. In order to control all of the parts of this robot, we chose to use the Atmega 2560 microcontroller chip. This chip was chosen due to its large number of GPIO pins which are needed to control the 5 motor drivers, parallel gripper, TFT display, Bluetooth module, and the fan heater. The Atmega 2560 chip also has 256 kilobytes of memory needed to store the large code size of this robot. All the components of this project operate at a 5-volt signal. Thus, a microcontroller that with a 5-volt pin operating voltage is needed. Again, the Atmega 2560 chip suits this requirement. Using the Atmega 2560 chip will allow us to properly operate all components necessary to perform automated pin transfers. Next, we have the microcontroller schematic. There are some additional circuitry accompanying the Atmega 2560 chip to allow it to operate properly, some of which include a crystal oscillator and some RC circuitry as chosen in the schematic. This circuitry is mainly for timing and properly configuring the onboard 16 MHz clock signal. On the PCB, it was decided to provide a regulator for both 5 volts and 3.3 volts, since the Atmega 2560 requires both of these voltages for proper operation. As a result, 2 separate circuits were designed to properly manage this. On the left, we have the circuit diagram for the 5-volt regulator, which take an input voltage between 7 and 12 volts from the USB to serial port, as well as a power jack. On the right, we have this circuit for the 3.3 voltage source below. The Atmega 2560 documentation, as well as some open source documentation from notable manufacturers such as Arduino and Espressif, were referenced in the design for these voltage regulators. Next, we have some additional circuitry used for debugging. Starting from the bottom, we have some voltage lines and a reset logic for the chip. When the reset button is pulled low to ground, the Atmega 2560 chip is shorted and power is restarted, which in turn resets the program on the board. Similarly, we have some indicator LEDs which are used to show the user whether or not power is on the board and if data is being transmitted between the board to the computer. We also have some solder pads which are used to solder physical wires onto the board, for example, the motor drivers or the LCD.
Our initial idea for a user interface was to use an LCD and keypad. We had considered trying to use a touchscreen, but we already had experience using keypads, and we already had all of the necessary parts to implement the keypad design, so we decided to go the keypad route. When we started to work on the UI, though, we decided to give touchscreens a shot. Getting a touchscreen to work ended up being not much more difficult than working with a keypad, and it looked much nicer than the keypad we had on hand, as well as all the other keypads we had considered. Not to mention that it was also cheaper, since all we had to do was activate the right pins to activate the touchscreen. We were using Hilotco's 2.4-inch 240 by 320 LCD. It is 3.3 volt and 5 volt compatible, meaning this LCD fits right in with most of our hardware, since most other parts also require 5 volts. The LCD also has 18 bits reserved for colors, but we only ended up using 2, just black and white. And then, to have the LCD be functional, 5 analog and 9 digital pins need to be connected. Of course, the point of the user interface is for the user to be able to interact with the robot. Specifically, we allow the user to specify the number of well plates they would like to run in a single batch, how deep the pin tool will be dipped into those well plates, and which watch steps they would like to run. We also ask the user to confirm their selection before moving on to the actual pin transfer process. During the pin transfer process, the LCD displays which plate is currently in use and what its location is. And finally, at the end of the batch, we ask the user if they would like to run another full batch.
The Pin Transfer Robot Progress Monitoring app is a companion app that is provided to the researcher to notify him or her on the progress of the robot. To use it, the user must tap the Scan button, select the HM10 BLE module, and simply tap the Connect button to connect to the BLE module. Once connected, the BLE module will send the plate number that the Pin Transfer Robot is currently on, as well as the state that it's currently in. The HM10 is a Bluetooth module that uses Bluetooth Low Energy technology to save power consumption. It also uses the master-slave communication model to establish half-duplex communication.
The LCD is using Adafruit GFX and touchscreen libraries, as well as the MCU Friend KBV library. The Adafruit library is what allows for graphics to be written to the LCD. In the example below, the TFT object in use is from the MCU Friend library, but all of the function calls are from the Adafruit GFX library, a result of the MCU Friend library extending the Adafruit GFX library. The touchscreen library is the other Adafruit library that we use. It allows for the when and where of a touch to be determined, which allows us to determine if a key on the LCD keypad has been pushed. The final library in use with the LCD is the MCU Friend KBV library. This library is what allows us to access the Adafruit GFX functions and write to the screen. Originally, we were using the Adafruit TFT LCD library, but due to hardware compatibility issues, we had to switch. The two libraries are nearly identical, except that the MCU Friend library does port switching to the Atmega 2560 port setup for us.
For this project, we decided to use the Excel Stepper library to interface with the motor drivers. Excel Stepper is an object-oriented C++ library for interfacing with motor drivers such as the DM542D that we're using in this project. It supports both precise manual control of the speed and acceleration of individual motors in both blocking and non-blocking function calls. Additionally, the library keeps track of the position of the stepper motor, such that once we calibrate each motor, the library will maintain exactly which step each motor is at. Now, I will review some of the important functions that were used in the making of the pin transfer robot. First, we have the calibrate motor function. This function works by having a single motor take steps towards its limit switch, and when the limit switch is hit, a few things happen. First, the number of steps taken to reach the limit switch from its initial position is saved. Then, the motor is stopped and the current position is set to 0. Clearly, stopping the motor prohibits the motor from moving any further, since there is no more space for it to move, and setting the current position to 0 for the motor ensures that the motor is at a home reference point. By storing the number of steps from initial position to limit switch, we can easily store each position the robot needs to be based on its distance from limit switch. Instead of using trial and error to determine which position the pin tool or parallel gripper must be in the pick of a plate, we can set the motor manually or where we want it and then run the calibration code to return the number of steps it takes each motor to reach its limit switch. All of the other functions in this code for the pin transfer robot uses the move to coordinate X and move to coordinate Z functions. These functions move the motor to a given coordinate in the three-dimensional space. However, the ordering of which motors move first are different. The reason for this is to avoid collisions on the workspace. In some cases, the Z-axis must be moved up first to avoid hitting a stack of plates or the cleaning solutions, where in other situations the gantry can move freely in the X-axis. Nevertheless, both of these functions perform the same goal in moving the motors to a given coordinate position in steps. Here is the main loop of the pin transfer robot's motor functions. After receiving input from the user, the run all cycles function begins by looping over the number of cycles. For each cycle, the function do cycle is called, and here the ordering of the function calls can be seen. As mentioned earlier, the flow of the robot's actions can be seen here. First, both plates are taken from their respective input stacks. Then a pin transfer occurs, after which the plates are put onto their respective output stacks. At this point, the pin tool can be washed and dried and be placed back to where it started from to begin the next cycle.